Let's continue our discussion. In the previous video, I discussed about the overcurrent protective device coordination by this time discrimination, and today's topic will be the overcurrent protective device coordination by this current. Yeah. By this current discrimination. So today I will cover this one. Fine. Let's draw one simple diagram here. Suppose this is generator, one circuit breaker. Here this is 11 kV breaker, and obviously this is 11 kV generator. Okay. Suppose here is the cable, let's put one transformer here. This is 415 volt. This is 415 volt pass, and here another breaker. Okay, so CB1, this is CB2, CB3. Okay, let's take these three CBs here. It will be sufficient to clarify the point. So today's topic is the discrimination of overcurrent protection devices by current. Let's say here is a fault. At 415 volt bus. So in that case this CB3 should trip first, then CB2 will come into the picture, and then CB1. So this should be the coordination, definitely, but this time it will be based on the current discrimination. Based on the fault current, the relay as well as the circuit breaker will trip. The relay will pick up and the corresponding circuit breaker will trip. Suppose here is the transformer, 11 by 0.415 kV transformer. So by current means here the circuit breaker should be set at that point based on this fault current. Suppose here the fault current is 16 kA and since the transformer voltage ratio is 11 by 0.415 kV, there is the transformer percentage impedance over here. So this transformer impedance will restrict the fault. It will pass the fault because the transformer has the short circuit withstand capability. So there will be a through fault current, but this fault current will be smaller than this low voltage side. Let's say for this 16 kiloamps fault current at 415 volt system voltage, here the transformer upstream side, that means at 11 kV side, this fault current, let's say 2 kiloamps. So this circuit breaker will trip based on this fault current, obviously after applying some margin over here, and then this circuit breaker CB2, that fault current will be less, suppose 2 kiloamps. So this will be set at a lower value than this side, because the fault is here. So the fault current will be more at 415 volt system, and the fault current will be less. The reflected, this is the reflected fault current. This 2 kiloamps is the reflected fault current at 11 kV side due to the fault in 415 volt bus. And this circuit breaker CB1, this will be coordinated with this CB2. So this coordination is based on the magnitude of current, not based on the time. Let's draw the TCC curve for this. So this side time and this side current. So for this, suppose for CB3, this depends on this current. This depends on current. So this is the current to this. Suppose next breaker, this is the current, and next breaker, this is the current. Okay. So for this is the current magnitude. So this will be coordinated based on the current only. Suppose in case of any fault here, in case of fault at transformer primary side, if there is a fault, here, then this fault current will be more. Suppose this fault current is 20 kiloamps. So this is 20 kiloamps. Here it is 16 kiloamps, and here for CB1, suppose this is 25 kiloamps. So based on the current, these devices are coordinated, but the main disadvantage with this current discrimination method is that this depends on the impedance, or the if the fault current, if the fault location, suppose this fault, if this fault location is far from the source, or there is a impedance, there is the considerable impedance in between the two protective devices, then this coordination will work fine. Which I want to say, suppose this transformer, for this transformer there is the transformer impedance, so it will restrict the fault. That's why the fault current at high voltage side will definitely be different, far different from the low voltage side. So in case of any fault here at low voltage side, if the fault current is suppose 16 kiloamps, based on the transformer impedance, the reflected fault current at 11 kV side, it may be as low as 2 kiloamps. That means if there is the considerable impedance in between these two circuit breakers, if I want to coordinate between these two circuit breakers, if there is the impedance, then this current discrimination method is good. But here if you look at this point, suppose for this generator breaker, and here is the 11 kV outgoing circuit breaker, if we want to coordinate these two circuit breakers, there is not much difference in the fault current. Suppose whatever fault current this circuit breaker or this relay will see here, the same fault current, almost the same fault current will be seen by this breaker as well, because suppose this is the 11 kV switchboard. So for this 11 kV switchboard, actually this is the 11 kV switchboard, so it includes this incoming breaker, this 11 kV bus, these outgoing breakers. Likewise there will be other outgoing breakers as well. So if we want to coordinate with these two protective devices, these two breakers, it is not possible to discriminate by current, because the fault current will be almost same here and here also. That means we cannot provide the proper coordination by this current discrimination method. So if there is any considerable amount of impedance in between these, suppose there is a cable, suppose there is a cable in between two circuit breakers, and this is far away, this 415 volt switchboard is far away from this 11 kV switchboard, and this is connected by this cable. That means cable is the fault resistance here, this because cable has the impedance, its own impedance. So the fault current at this 11 kV side, the fault current, sorry, this is not 415 volt, definitely this is also 11 kV, because there is no voltage step up or drop down. So that means this is the outgoing feeder. Suppose this cable length is 1 or 2 kilometer, so it will provide, this cable will provide the considerable amount of impedance between these two switchboard breakers. So in this case, the fault current here and the fault current in this location will be different. So in that case, this current discrimination method may also be applicable. But for the faults nearer to the very close to two or more protective devices, this current discrimination method is not useful. So that is the main disadvantage of this current discrimination method. Now what's the solution? For the solution, we need to